In the realm of visual representation, self-supervised learning has primarily concentrated on identifying and distinguishing content features within images and videos. However, this approach often overlooks the dynamics of motion and spatial positioning. To bridge this gap, the authors present MC-JEPA, a novel method that integrates the learning of optical flow, essentially the motion between frames, with content features in a unified framework. By utilizing a shared encoder, this technique allows the two tasks to enhance each other, leading to richer content features that effectively include motion characteristics. The performance of MC-JEPA stands strong, matching existing benchmarks for unsupervised optical flow and self-supervised learning measures in downstream tasks like semantic segmentation. This holistic approach signifies a promising advancement, laying the groundwork for more sophisticated self-supervised learning methodologies that can adapt across various visual tasks, from motion prediction to content analysis. The initial segment of the method section provides an in-depth look at the architecture and techniques employed in the study's optical flow estimation and multitask learning. MC-JEPA architecture. The proposed method, known as MC-JEPA, integrates motion learning through optical flow estimation from video data and content learning via joint embedding of image views. A crucial element of this system is a shared encoder, indicating that both tasks leverage a common set of learned features, thus promoting efficiency and coherence across learning objectives. The optical flow estimation part of the architecture is based on PWCnet, a model recognized for its multi-scale analysis of optical flow. Given a pair of consecutive video frames, specifically the frame at time t and the following frame, this system begins by extracting features at multiple resolutions. The encoder generates pyramidal features, essentially hierarchical representations of the video frames, allowing the system to capture details at different levels of abstraction. The optical flow is calculated using a coarse-to-fine strategy. It starts with the initial, low-resolution features and progressively refines the flow estimation at each layer. Initially, a coarse flow estimate is computed and used to warp the features of the second frame, which are then compared with the actual second frame features through a regression loss metric. By iteratively refining this flow estimation and utilizing techniques like loss comparison between warped and actual frames, the system improves the accuracy of motion representation. To enhance the robustness of this estimation process, the cycle consistency losses are introduced. These losses strive to ensure that the estimated correspondences between features from the first and second frames remain coherent, effectively reinforcing the accuracy of the flow calculation by minimizing discrepancies between transformed features across all layers. This training framework poses stability challenges when implementing a joint learning approach, thus necessitating the use of variance-covariance regularization across each feature layer. This regularization helps keep the training process stable, reducing fluctuations during the learning phase. Related work. The subsequent section discusses advancements in self-supervised learning, primarily established through various techniques aimed at creating invariances to data augmentations. It evaluates contrastive methods that emphasize completing groups of similar visual features, as well as clustering and non-contrastive methodologies that focus on maintaining structural integrity within learned embeddings. The exploration of optical flow estimation traces its roots from classical optimization methods, evolving to incorporate deep learning techniques. The paper highlights unsupervised learning as a promising avenue, benefiting from photometric consistency, which ensures that the transformations of video frames align visually. This section establishes a foundation for understanding the context of the proposed approaches, emphasizing how the combined learning tasks reinforce one another while navigating through the complexities of optical flow and self-supervised learning paradigms. It opens the door for a further exploration of the proposed approach and detailed methodologies that will be delineated in the subsequent sections. In the second part of the method section, the authors delve into the technical details of their approach for estimating optical flow and incorporating self-supervised learning through a multitask framework. Regression and smoothness. The authors employ a sophisticated hierarchical flow estimator named PWCnet, adapting it to their custom encoder architecture. The estimator works by taking sets of features from two consecutive images, denoted as X, T, and X, T+1. From these, an initial flow estimation is made, which is progressively refined at higher resolutions. This means that the method first makes a rough estimate and then improves it step by step. The core of this estimation involves a function denoted as f, which takes these features and estimates the flow between two time points. Once flow is predicted, the authors utilize intermediate predictions and apply a multi-scale loss to ensure consistency across different layers of the encoder. The regularization needed to ensure smoothness in the flow is captured through a function that penalizes abrupt changes in flow, especially in regions with little texture. Cycle consistency. To enhance the reliability of flow estimation, the authors introduce a cycle consistency loss. This means that for an estimated flow from image I, t, to I, t plus 1, when they map it back to I, t, the result should resemble the original features from I, t. This is important because optical flow isn't symmetrical. Not all pixels in one frame will map to the next frame equally. The loss function defined promotes this bidirectional consistency, which helps in mitigating problems like occlusion. Variance-covariance regularization. Additionally, a variance-covariance regularization method is introduced to stabilize the training of the shared encoder across multiple tasks. This involves calculating both variance and covariance of the features, which helps control the distribution of the learned representations and enhances performance. Multitask self-supervised learning. The authors then explain how they integrate content learning with the optical flow estimation tasks. By utilizing techniques from recent literature, they generate different views of the same image through transformations like cropping and color jittering. These views are used in conjunction with a loss function, vi-cireg, which not only encourages similarity between views, but also helps maintain diversity among feature representations. During training iterations, the authors draw sequences from a video dataset for flow estimation and images from another dataset for self-supervised learning. They compute respective losses for each task and combine them, indicating that the encoder processes both tasks concurrently, thus fostering synergy between them. This approach leads to a final comprehensive loss function that takes into account all loss components, paving the way for the experiments and validations that follow in the next section. The experiments section meticulously delineates the experimental framework used to evaluate the model's performance, with key insights drawn from various datasets and methodologies. Initially, the model was pre-trained using multiple optical flow datasets, including KITTI and MPI Sintel, as well as ImageNet 1K. Evaluations were conducted on flow estimation, instance segmentation, and video segmentation tasks, notably utilizing the Davis 2017 benchmark. In the main results, the efficacy of the model, MCJEPA, for optical flow estimation was assessed against state-of-the-art methods. Results compiled in Table 1 highlighted competitive performance, particularly when juxtaposed with UF flow and AR flow, while surpassing MCRW, which shares similar goals. Although SMUF outperformed the model, the primary goal was to leverage flow estimation as a mechanism for broader feature learning. Progressing to instance segmentation, the model showed a significant enhancement over previous methods, such as MOCO v3 and vi-cireg. The results suggest that employing flow estimation as a pretext task substantially improves localization capabilities. The performance on video segmentation tasks indicated that integrating flow estimation into training robustly bolsters content feature learning. The ablation subsection delves into fine-tuning various components. Table 2 scrutinizes the impact of diverse pre-training datasets, identifying that multimodal training enhances flow estimation without detriment to segmentation tasks. Table 3 offers insights into flow estimator architecture, elucidating that layer norm significantly stabilizes training, as opposed to L2 normalization. Subsequent explorations included variations in backbone architectures, Table 4, and strategies for data sampling, Table 5. These explorations highlighted the superiority of the Xiaowen-VNXTT backbone and demonstrated that optimal training strategies involve a combination of batch alternation and loss amalgamation. Ablations further assessed the initiation of flow estimation relative to ImageNet pre-training, confirming a delay post-initial epochs yields efficiency without sacrificing performance. The interplay of cycle consistency and multitask balancing was examined, revealing nuanced tuning is essential for maximizing performance across both flow estimation and segmentation tasks, ensuring an adept balance between the dual learning objectives. This lays a robust foundation leading into the concluding section of the paper. Conclusion. In this research, we presented MC-JEPA, a groundbreaking multitask framework for learning motion and content features through self-supervised learning and optical flow estimation. The model demonstrated strong performance across diverse tasks, including optical flow estimation and image/video segmentation. We believe that our approach promotes the utilization of multitask learning within self-supervised frameworks, paving the way for feature generalization applicable to various downstream tasks. Future research will focus on expanding this model to larger datasets of natural videos, aiming to capture both short and long-range interactions hierarchically. Ultimately, this work signifies a step forward in understanding and leveraging self-supervised learning for motion and visual content representation. Our findings set a foundation for further exploration and development in the field.